this to come up. The PowerPoint, I know you're in there. There we go. All right. Everything's taking a long time. All right, any questions for anything we've done so far? Okay. Now, this section 1.3, starting this today, we're really talking about mathematical models, okay? We're not going to hit this really badly or heavily. I'm trying to think what was in the syllabus. Don't think there was anything about mathematical modeling. I think it was, oh boy, what do they call that? Numerical methods. And that's not the same. So let's just hit this quickly. What is a mathematical model? Okay? Now, some of you have had some physics. Have all of you had some physics so far? Yes? Okay. Have you heard of Maxwell's equations? Electricity, magnetism? Maybe you're not there yet. They're pretty far into electricity and magnetism. What Maxwell did is James Clerk, it looks like it's Clerk, but he's Scottish and they pronounce it Clark. Maxwell came up with something that unified. They knew electricity and magnetism were related to each other. They interacted with each other, but no one knew how. He came up with a set of, now he used differential equations, what we're doing here. Partial differential equations, we're not doing those here. But he basically set up the framework by which electric fields, magnetic fields interacted. Like several decades before they had the technology to test what he had proposed. And he came out right on the money. I mean, he did a great job. So he did a mathematical model of a pretty complex environment, which was electromagnetic radiation. And he basically set the tone for that in some models before they could ever have the technology to test those models. Okay? So that's what we mean by that. Now, construction of a mathematical model with a system starts with some type of identification of variables responsible for changing the system. We may choose not to incorporate all the variables into the model at first. In this step, we specify the level of resolution of the model. In fact, how good or how sorry are you willing to live with, okay? Does it get close? Is that good enough? Or do you want it to be right on the money? Usually start, just hitting toward the general area. We make a set of assumptions, hypotheses, about the system we're trying to describe. And they have a little diagram in the book. If you don't have the book, it's not worth doing too much on. But the solution gives the state of the system, in other words, at the point where you're willing to accept it. And they have several examples, population dynamics. I will hit a little bit there because they actually write some things. So let's do this. Let's think about population dynamics. How fast can a population grow? You can think about people population or microbial populations or insect populations or even plant populations. What determines how fast a population can grow? Just in general. Say again? A little louder. Huh? Okay, you're talking about birds. Okay. I think you hit it right on the nose. A population is going to grow very fast if there's not many there to begin with. If you have one mating couple of birds, plants, whatever, you can only produce so many offspring, right? So that population is going to be pretty slow growing. But if you have a pretty large population, then it can grow much more rapidly, right? So the rate of growth of population is proportional to how big the population is. So here's something, and let me get my pen activated. okay? The rate of growth of population, dP dt, how fast the population grows, is proportional to the size of the population. That kind of makes sense, doesn't it? If you inoculate a medium with a single bacterium, after however what the lifetime of bacteria that bacterium is, it's going to double. But if you inoculate it with 1,000 bacteria, you're going to have, in that same period of time, you're going to have 2,000 bacteria. So, yeah, the rate at which it grows depends on that. Now, that symbol there is proportional to. It's a pretty ugly symbol, but in the book it's a little nicer. If we want to make that an equation, what we do is dP dt is equal to some constant, and they use K, the German constant, okay, times P. Now that changed the proportionality to an equation, and you can do that anytime. If you know something proportional to it, just put instead of proportional equal or constant times it, okay. Now, radioactive decay. You know what? I may be breathing in some radon right now. Could happen. Radon is everywhere in our atmosphere, just at incredibly low concentrations. Okay? If I happen to breathe in some radon right now, did I say radium before or radon? I meant to say radon. Okay. Radon, good. Okay. If I breathe it in, radon has a half-life of about 4 days, which on the bad side means that it hangs around for about 4 days and could still be disintegrating and producing radiation particles that could do you harm. But on the good side is, unless I'm right at the end of that 4 day for that radon I breathed in, there's a good chance I'm going to breathe it right back out again, okay? Because it has no reason to stay in my lungs. I mean, oxygen has a reason to be there. Nitrogen doesn't. I breathe it in, I breathe it out. You know, carbon dioxide, I breathe it in, I breathe more out because I'm expending some. You know, methane, I breathe it in, breathe it out. Radon, same thing. Unless it happens to be that it happens to undergo radioactive decay when it's in my lungs. If that happens, then it could do damage to my lung tissue. Now, if there's not very much of it, maybe my lung tissue can repair that damage before anything goes terribly bad. But if I'm in a very high concentration of radon gas, there's a lot more probability that some of that radon I'm going to take in will be right at the end. It's going to radioactive decay while it's in my lungs, and while the lungs are trying to repair the tissue there, it may have some more somewhere else, and after a while I can't repair it fast enough, and now could be a cancer starts. Okay, so if you're in an environment with a high level of radon gas, there's a better chance you're going to get lung cancer result. It's not going to be immediate. Okay, it'll be years down the road. You might not even remember you were ever in an environment. You might not know you were in an environment with high, but it could happen. I wonder about Dr. Wilson. I don't know if you know her. She's never smoked, as far as I know, a day in her life, and they discovered lung cancer. So they're taking care of it. They caught it very early. So yeah. But anyway, very similarly, the concentration, the rate at which radioactive decay occurs, dA dt, is proportional to the amount of material you have, radioactive material, okay? The rate at which that's happening. Make that into an equation. dA dt is equal to K times A, or some other thing, okay? Yeah, Wilson, yeah. Yeah, she's not at school this term. She's probably already had the surgery. We don't know for sure. But they caught it early enough that they don't think she's going to have chemo or radiation. They think they isolated the tissue, got it out. And they did arthroscopic surgery so she didn't have to be opened up completely. Or at least that's the last I heard. But yeah, it's came as a shock to everybody. They found out over Christmas break. It was bad. I mean, good they caught it early, but it's just such a surprise. Okay, a single differential equation can serve as a mathematical model for many different phenomena. Like this one, how do you know whether you're talking about population growth or radioactive decay? You don't. Same differential equation solves them both. It's the same techniques you use. Now, the constants may be very different, but, you can deal with that. It's just a constant. Okay. Here's another one. Newton's law of cooling or warming. The rate of change of temperature, okay. By the way, if you're not used to it, capital T is temperature, little t is time. So the rate of change of temperature is proportional to the difference in temperature between T minus, and they call it T infinity. It just depends on what you're talking about. The next one actually says it a little better. Take that one and do the same thing, change the proportional to a constant. You get dt, which change temperature with respect to time is equal to k times this. And why in the world I'm sorry, that's not an infinity. I wondered why they put it in infinity. I couldn't read. That's an M. Okay, sorry about that. T minus Tm. Now, they didn't tell you what M was. What's that? Yeah, that's what I would call the ambient temperature. But I was trying to think of why they named it M. Median, I don't know why they call it M, but it is, that's surrounding. This is the thing that got hot, and how fast is it cooling? It depends on the temperature around, okay? If it's, and this works for heating or cooling, let's just say that I have an object I've heated to 150 degrees Celsius. If it's 100 degrees out there, it's going to take a lot longer for that to cool than it would if it was 20 degrees outside, okay? Because the difference here, this difference is what determines the rate at which it cools, okay? So it's the same type of a deal. Spread of a disease, which basically is almost a population study. I'm just giving you samples. I'm not sure this section is really worth a whole lot, except just giving you ideas of how differential equations are actually used all the time, okay? So it's not just, boy, this is another discipline I have to sit and learn. No, these are practical, okay? Disease, dx dt, I can't write. Let's see. X is the number of people who have contracted the disease. Y is the number of people who have not yet been exposed. Then it seems reasonable to assume that the rate at which the exposures will happen, at which the disease spreads, is proportional to, which we're going to go on and say, equal to k times xy, okay? Now, I don't know if that makes a lot of sense to you. Why would X is the number of people that have been exposed, Y is the number of people that have not, okay? Well, if not many have been exposed, say you're in a group of 1,000 and only one has been exposed, the rate at which that person is going to interact with others is going to be pretty small, okay? So that would be the case that X is small, then the rate's going to be small, no matter how big Y is. But on the other hand, if you had 1,000 people and 900 had been exposed and 100 haven't, the rate of exposure can't be very great because there are only a few people that can still be exposed. Because you're not going to expose those that already have it, okay? They already are exposed. So that would then, the Y would be small and the X large, and it would still be a small rate. It's only when you got a large number exposed and a large number non-exposed, then you're going to have a very rapid increase of disease. In fact, diseases follow a curve, they call it a logistic curve. At the beginning of the disease, it's pretty slow getting started, but boy, when it catches hold, especially if it's a very virulent disease, it can increase like crazy, and then once most of the population has been exposed, then it levels off, okay? And quite often you'll see those logistic curves. My wife is an epidemiologist, she studies diseases, and they use logistic regression to model their diseases all the time. It's a statistical term. We're doing the analytic stuff, but that's what you got. Okay? Now, suppose a small community has a fixed population within people, then the X and Y are related to each other. X are the ones who have been exposed, and say N minus X would be those who hadn't been exposed, right? So then you could adjust that equation, and here's another example. The X in that states in a small population, then this would be is equal to K X times, now they do something a little strange here, N plus 1 minus X, okay? If one infected person is introduced into that community, then that's what you get. You get that one extra person in. It's a small community where, yeah, so if you have one more person come in, N plus 1 minus X. Rather a strange way to do it, but it's doable. So you see, now you get down to one variable, okay? And you go from there. Chemical reactions are basically follow differential equations. Now, none of the chemistry we teach here requires differential equations, but if you were to get into chemical engineering, of course, and really advanced chemistry, you probably are going to need differential equations there too. Here's just an example. Boy, this is going back to long time chemistry ago. Let's do this one. CH3 CCl plus NaOH goes to CH3 COH plus NaCl. Now, you see, I'm not big on organic chemistry, and this is organic chemistry, but this is, they're saying here, T-butyl chloride. And we're not going to get into what T-butyl means, but basically, a CH3 in my mind is a methyl group, but they're calling it butyl, so this may be a more common name. CCl, okay, that's the chloride part. So this is C-butyl or T-butyl chloride plus sodium hydroxide, a very strong base. Interact those and you get an alcohol, T-butyl alcohol plus NaCl, salt, okay? Now, there's a part of me that wants to draw that for you. I'm not sure you want me to, but this is what it looks like. You have that center carbon, that's that one, and carbon has 4 bonds on it. This one has a carbon to it and then 3 hydrogens around it. Here's a second one with a carbon and 3 hydrogens around it. And the third one has a carbon with 3 hydrogens around it. And I would have called those methyl groups. They're called them butyl groups. And then that's the carbon, and then you have a Cl over here. Okay? And then you have an NaOH here. OH is a what do you call that? It's an ion. Treated as, I can't think of, SO4, COH, CO4. Those are all, they have a name for that, a radical, okay, that's attached to it. And what happens here is pretty clear. The OH replaces the Cl. And then you wind up with, on the other side, you get the OH here and the Cl here. Sodium chloride is salt, and this turns into an alcohol, okay? Now, so what? Okay? What it says here is only the concentration of T-butyl chloride controls the rate of reaction. But in this reaction, CH3Cl plus NaOH, and that's going to CH3OH plus NaCl. Okay, same type of deal. 1 molecule of sodium hydroxide is consumed for every molecule of methyl chloride. That's what see, I knew that was a methyl group. That's called methyl chloride there. Okay. And the difference is that C in the middle is what changes it to a butyl. Okay. This is just a methyl chloride. 1 methane, except you substituted instead of an H, you substituted a Cl. Okay. So I don't know what the point is here. But anyway, then you can talk about the concentrations. And you'll need to read it. Basically, I don't want to spend too much time on this, but dx dt, again, it's the time rate of change, and x here is your amount of the chemical, whichever one you're dealing with, T-butyl chloride or methyl chloride, whatever you're dealing with, sodium hydroxide, whatever is the rate limiting factor of this, if that's the amount of that chemical at a time, and if alpha and beta are each in turn the amounts of the two chemicals it's reacting with, then dx dt is proportional to or equal to k times alpha minus x, because that's the difference of those, times beta minus x. Okay. Without going into great detail, that's showing that the amount of x you have is proportional to how much excess alpha you have times how much excess beta you have. That's one way of looking at it. It's not probably the best way. But it's not just how much X you have, but how X relates to the other two compounds in the reaction. Because you've got several things going on here. As you're making more of one, you're losing the other, and vice versa, you know. So, and as more substitution goes on, you get more of the other. So this is an example of how a differential equation could be impacting a chemical reactions, or you model chemical reactions with those. Now, I don't know if you've ever done these before, but mixtures, that's a classic example of doing differential equations or using differential equations. Not everybody has a book, so let me sort of model this here, okay? Here is your input into a vat, okay? Okay, and you also have a drain down here at the bottom by which you got water going out. So you got something coming in, you got something coming out. Okay, the something coming in is being mixed with whatever's in there to begin with. Okay, So this coming in is at one concentration. You got a different concentration coming out here. Okay? Now, the amount of the something that you have here, they do that as dA dt. The rate at which your concentration in this solution is changing. Okay? That's equal to the input rate of the salt minus the output rate of the salt okay? So that would be R in minus R out. Okay? Now, they go through some samples of putting in some values there of calculating the rate in. They don't really give you the numbers here. So let's say that, okay, yeah, they do. Here they are. I was looking for it up here in the picture. Your input rate of brine, this is salt water, is 3 gallons per minute. So you got 3 gallons per minute coming in, okay? Now, your container here contains an amount that's constant, and this is a constant 300 gallons. You're not letting that get any bigger, and it's not draining out. It's a constant 300 gallons. You're mixing that's coming in, and so your output rate, if you're keeping a constant 300 gallons, you got an output rate of 3 gallons per minute also. Okay? If you're keeping a constant amount in there. Okay. Now, they give you some numbers here. If the rate of the input, the concentration of salt in the input, so concentration in is 2 pounds per gallon. Okay. The rate of flow in, then that's your rate, is gallons per minute, 3 gallons per minute. The gallons go out, and you're adding salt of 6 pounds per minute. Because 2 times 3 is 6, gallons go out, pounds per minute. So this is the rate in would be 6 pounds per minute. Okay? Now, the rate out, they don't make this easy, okay? At any time t, and they don't have this written anywhere else, at any time t, you have A of t, the amount of salt in those 300 gallons, okay? You don't know how much it is, okay? But the amount of salt you have in there divided by the 300 gallons, this will be pounds per gallon of salt, okay? The amount of salt in pounds divided by 300 would be 300, or A over 2 divided by 300 pounds per gallon. Your output rate is 3 gallons per minute. And again, you can cancel out the gallons, and 3 will go into 300, 100. So your output rate is the amount that you have in there anytime t, and that varies. It changes. That's why you have to have it as a function over 100. Okay. So that is the rate out. Well, if your rate in is this, minus your rate out is this, this is the change, dA dt, that you're meeting there. And then we haven't learned how to solve those differential equations. This is just showing you how circumstances in which you would use it, okay? Now, Now, in this one, I know I've got it sort of messy here, so let me get some of this out of the way so you can see it a little more clearly. I'll take some of this scratch out of there. Ooh, that's not the scratch I wanted. Well, let me get that out. Okay. I'll go back and write what I just had, and I messed up by taking too much out. Okay. All right. What I just had was dA dt is equal to 6 minus a over 100. Remember, a is a variable, okay, function of time. Well, not picking up the eraser. Okay. Now, what they do with this, and this is typically what we do, we get dA dt minus, or plus, because you're adding that to both sides, a over 100 is equal to 6. That would be a differential equation we would solve. You wouldn't want them on opposite sides, you want them on the same side, a constant on the other, almost like equations. They are equations, but you're dealing with differentials, derivatives. Draining a tank, Torricelli's law. Now, the one reason I'll stop a moment here, there is a law, a name, you can write on Torricelli, you can write on how he developed that law, you can write on places where you use Torricelli's law, but this is Torricelli's law and how you go about draining a tank. And this is through a sharp-edged hole at the bottom of the tank. And without any, let's see, I'll just make a few minor modifications here. We're not adding anything. Oops, took out too much there. Okay. What we've got is we've got a constant flow out, but we start with the tank totally full. Okay, so let me go over here and erase this. This is actually a law in physics or engineering, wherever you might choose to use this. Torricelli's law. By the way, y'all done any measurements of pressure, atmospheric pressure, those kind of things? Problems with those? Okay. There's many ways you measure pressure. Pounds per square inch is the one we used to use all the time. Now metric is here. Kilopascals, which is a unit of, or pascals, or kilopascals, a unit of pressure. Atmospheres is a unit of pressure, but you also use sometimes the unit torr, T-O-R-R, named after Torricelli, I think. You can check me on that, but I'm pretty sure. So he did more than drain tanks, okay? He did a lot. So this Torricelli's law is this one. The rate of change at which the volume is changing, time rate of change of the volume, is equal to minus a sub h times the square root of 2gh. Okay? Now, what's your a sub h? Is the area of the hole of the tank. This is your a sub h, area of the hole. G, of course, is the acceleration due to gravity, and h, I'm pretty sure, is the height of the tank. Okay. Again, you don't have to memorize these or learn them and stuff. It's just another example of how we use differential equations, basically all the time. Now, in E&M, I know y'all have done Ohm's Law and Kirchhoff's and all that kind of stuff, right? Have you done anything with capacitors and inductors yet? Not yet. You're getting there, okay? Frankly, when you introduce either capacitors or inductors, what you wind up doing is introducing, in some senses, a differential equation, okay? I think I'll go to a clean slide to show this. Again, we're not doing these in great detail, just introducing you to the concept. So if you have a voltage source here, it could be, let's see, this I think would have to be, well, I want to say it'd have to be AC, but maybe not necessarily. Here's E of t, and it goes first through an inductor, then through a resistor, and then through a capacitor. This is an inductor, which is L, resistor, which is R, and a capacitor, which is C. This is called an LRC circuit. It doesn't matter which order you have them in there. That's not where the name comes from. You just usually call it that. The inductor itself, the inductance L, measured in henries, that's the unit for it, and they have a little h for henries. I was almost certain that's a capital H. I think this is a math book and they have that wrong. But I think it's capital H for henries. The voltage drop across an inductor is, the voltage drop across is L di dt, where I is current and T is time. There you have a differential equation. If you got it in there, it's there. Your R is just a resistor, okay? So the voltage drop across it would be IR, okay? I is current. The voltage drop across a capacitor is 1 over C times Q. Okay, but what is Q? Q is charge. Okay, but how does that relate to current? Well, dQ dt is equal to current, so actually Q would then be an integral of the current. So here in this thing, you have a derivative up there, a constant over here, not constant, but a constant multiplied by, and then this, you basically have an integration, okay? You think you're doing all sorts of things with that, okay? Now, in Kirchhoff's second law, okay, well, okay, let's go back to this. Here, you don't like to have integrations and derivatives in the same circuit. So here, like I said, I is equal to dQ dt, right? Current is amount of charge per unit time. That's what ampere is, okay? So instead of an equation with a derivative of a current, and then the integral of a current, no, we don't like to have that. Let's get everything in terms of this. Well, I is dQ dt, so di dt would be T2 I dt squared. So guess what you have now? Your Kirchhoff's law around here, you would have E, that's how much your voltage goes up, minus L d2 q dt squared, that's your current, change your current, minus R times dQ dt, that's your current, minus Q over C. That's your drop because of your capacitance. And then you can use Kirchhoff's law there. But what have you got? You got a differential equation. Those simple little Kirchhoff's laws you did before with just voltages and resistance, you're calculating for current without doing derivatives of a current. That turns a fairly simple equation into a differential equation. if you have resistor, capacitors and inductors in the circuit. Okay? And this would be equal to 0 according to Kirchhoff's law, which then you could write E is equal to L d2q dt squared minus plus R dq dt minus Q over C. Okay, plus Q over C. Moved it to the other side. They actually wrote it reversed, so you have the differential part first and then your constant on the other side. Okay, we're not solving any of these. You're just seeing how they set up and how they work. And I know you've done the motion part of it, where you have, say, good old Galileo's rock off the Leaning Tower of Pisa. That's everybody's favorite, most people's favorite. Newton's second law could be written as, we think of it as F equal ma, right? Where the force is the weight, mg. And one of these is negative. For some reason they put that negative, okay? Well, what is acceleration but m times d2, do they use y? No, s over dt squared is equal minus mg. And the m's go out, yeah, you can go from there, okay? d2s over t squared. The acceleration of the body is minus the acceleration due to gravity. Yeah, we knew that. Give it some initial conditions, you got your whole problem set up there. Okay? Falling bodies with air resistance. Okay? Galileo was somewhat responsible for this. You have the concept of viscous damping going on here too. That could be a paper topic. But basically, when an object is falling with air resistance, it's not just the mass times the acceleration, which is dv dt, okay? We used to say that was mg. That's just the weight pulling you downward. But if you also have air resistance, then you got a minus kv, where k is a constant that depends on the viscosity of the fluid in which you're going, and v is the velocity. So when you're falling through air, yeah, you're falling at the acceleration due to gravity, except for the air resistance. And that's why we use what when we're falling through the air? Parachutes. You now have a lot of air resistance, and that slows you down, so you're going at a constant speed. Your terminal velocity is very slow then. Without the parachute, you get pretty fast, and you don't have a fun landing, okay? With parachutes, sometimes that can be a little less than fun too, but at least that should be enjoyable. But the other thing, what if you're falling through molasses? Boy, that K is huge then. That's going to slow you down big time. You're really going to go at a slow rate because you have a large viscosity, okay? So, another example, differential equations. Okay. Suspended cables. There's a lot of terms here. Basically, the differential equation turns out to be this. dy dt, no, I'm sorry, dy dx is equal to w over t sub 1. Now, I'm sorry, t sub 1, okay? Now, to me, that's got a lot, there's a lot that's been left out here, because you got all sorts of pictures before, but they tell you what T1 and W is. T1 is T2 cosine theta, and W is T2 sine theta. if that's indeed true, then the T2s go out, and so, never mind, I don't think you usually would do that. Your tan theta would then be that W over T1, and you go on from there. Just lots and lots of applications. Again, you don't need to be able to reproduce these, but just to recognize it. Now, they have a little cartoon-looking thing at the bottom. Differential equations, you can do them analytically. That's most of what we're going to be doing in the test. That's what this is about, analytic solutions. You can have qualitative solutions. That's estimates. Let's say this is going on. What do you think it's going to be here? Okay? Or you can have numerical. Okay? And then you set up and go. We're going to introduce that, maybe touch on it, but we're not going to spend lots of time on it. We're going to focus on the analytical part. If you got that, you can sort of figure out the rest of it. Okay? Then they have remarks at the end talking about dynamical systems, state variables, state of a system, response of a system. I don't want to say we're not going to use those terms very much, but if we use them a little, you might want to remember, come back here and get their definitions. Okay? Now, what do we do with homework exercises here? For population dynamics, you can do any of the odds, one or three, either one or three or both. And it's not really asking you to solve anything, but sort of set it up and think through it. Nature's law of cooling warming, number 5. Okay? You have a graph there that you might be able to help you with that. Spread of disease, number 7. Mixtures, either 9 or 11. Draining a tank, Torricelli's law, 13. Series circuits, and these with not just resistances and batteries, but now you have inductances and capacitances. That's number 15. Following bodies, 17. Newton's second law and Hooke's law. By the way, those two guys didn't like each other very much. They started out okay and maybe came back together at the end, but in between they were not the best of buds. That would be number 19, Newton's second law in rocket motion, 21. Any of you go to, some of you were here at Dr. DeLucas' presentation Monday, weren't you? Yeah. He did some stuff on rockets, remember? Okay. And Newton's second law and law of gravitation, that's note 23. And then there's others, and you can look at any of these that you're interested in or not. Learning theory, infusion of a drug, reflective surfaces. And then there's some just to think about and talk through. Don't expect any of those on tests. But if you're interested, there's any of those 31 through. I'm not saying all these answers are in the back. I would check before I did too much. Following bodies, that kind of stuff. There's plenty here. Now that finishes chapter 1. What does that mean? I was debating whether we do a test on chapter 1, and then last term I did 1 and 2 together because 1 was so short, but it took us forever to get through 2. So I'm thinking I'll give you a pretty short test on chapter 1. Should be pretty easy, and you can just do that, and then we'll start 2 anew, and we can then focus a little bit more on that. I don't have it ready now. I have part of it ready, but I don't have it completely ready. I'll try to work on that some. I have a little time today, but I've got a field trip tomorrow, so I've got to get that ready. So I probably won't be able to work on this until I have very little time tomorrow because of the field trip. And then Friday I'll be on Birmingham campus, and we've got to be working on schedules and stuff. I may not even have it ready for you on Monday. I'm sorry. It may be Wednesday before I have it ready. because it may be Monday before I'll be able to even do much on it. So, anyway, so again, it's a take-home test. All the tests are take-home tests. Okay, so also at the end of the chapter, they have a review section. The odd number problems have answers in the back, so you can work on any of those odds that you see in there. All right. So let's move on to chapter 2. First order differential equations. All right. Time out. You tell me, what do we mean by first order? What does order mean? Say again? Yeah, derivatives. First derivatives only. Second order, we may have second derivatives and first derivatives in it. So a first order differential equation only has first derivatives in it. Only. Okay? What's that now? No y double primes. Y prime and y's and x's. Okay? But no y double primes. Y double prime second order. Okay? That's it. So, chapter 2 is first order differential equations. Now, again, the first part here is sort of nebulous, sort of touchy-feely stuff. I hate starting chapters this way. You know, it just, you talk and blah, blah, but you never do anything, okay? So let's try to do it quickly. Some fundamental questions here. I think I'll clear the page here so you won't confuse it with the other stuff, okay? In section 1-2, whenever f of xy and partial of f with respect to y satisfy certain continuity conditions, that's that stuff we were doing last time, which is sort of blah, 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 blah. Anyway, here's the punchline. A derivative dy dx, okay, of a differential function y, of a differentiable function y, of the y, which is some function of x. Now, in differential equations, remember in back in early calculus, they never wanted you to use that. They say y is f of x or g of x or something like that, but you didn't want you using the variable as a thing. We don't care in differential equations. We know you're so used to this stuff that you can say it that way and understand it. Okay, what does a derivative do of some differentiable function? Y is equal to y of x. This is change of y over change of x. What's change of y over change of x? Delta y over delta x. Slope. First derivative gives you the slope of the function at that point, right? So, that's exactly what we've got here. Dy dx is equal to some f of x and even y's. Y's can be in that too. Then, that is a y is equal to y of x can be a solution of that differential equation. Okay. Now, sometimes we don't know beans about that differential equation. But what we do know, if you know this, that dy dx is equal to f of xy, that's your differential equation. So without solving it, at least what you can do is give me a point. Okay, you know f of xy, so you plug in your x, you plug in your y, that puts you right there. And you know that derivative right there, when you evaluate it at that value, say x equal 7, y is equal 9. So you plug in f of 7, 9. Whatever that function is, plug in the numbers, that gives you something. And if you know dy dx is equal to that, guess what? You know the slope right there. That slope may be large positive, gradual negative, 0. You know something about the function there. You know what way it's heading and about what. And the magnitude of that is how fast it's heading there. Well, no, that is the slope, sorry. That is the slope, that value. Okay. So with that in mind, and I cannot draw these on the board. So you don't have a book. Yeah, you don't have one either?
I was trying to get online.
Yeah. Okay. You too? You've got it online already, right, Matt? Okay. So I'm going to do the best I can here. Okay. Now, what you have here, if you know that dy dx is equal to sum alpha of xy. So if you pick a point, xy, plug it into that function, alpha of xy, calculate it. If it's slightly positive, it's going this way, very positive, it's going the right way, zero, it's going this way, slightly negative this way, more negative that way. You got the general gist of it, okay? And if you plug it in and get those little arrows at lots and lots of those points, and frankly, you have a computer do that for you. You don't want to do this for, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 by 15 calculations. Maybe you got plenty of time on your hands, but if not, get a computer to do it for you, okay? And it gives you the slope at every one of those points. And then what you do is, remember when we said you had a family of solutions? If this is what you get all over space, we just did the first quadrant here, it looks like. And if you have one line that comes down and does like this, another one that does like this, another one that does like that, that's your family of curves. And guess what? Between any two curves, there's an infinite number of more curves you could put in there. You're just picking certain values and going for it, okay? Now sometimes they don't draw those in, they just have this. Well, what does this look like? This looks like you got a field going like this, and up here you got a field going like this. I don't know, is that a magnetic field or something? That's, actually they did give what that one is. That function is dy dx. This is example 1, and maybe I should do example 1. So what I'm going to do is this. I'm going to use their graph, and here is the function dy dx is equal to 0.2 xy. There is your differential equation. Now we aren't doing anything about solving it. We're just trying to get an idea of what's happening to it. Okay? Now, what's that value at 0, 0? 0. It's just a point there. Nothing happening there. In fact, all on the x-axis, where y is equal to 0, it's 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 0. In fact, it never even touches there. I don't guess, okay? It's just points there. Now, when x is 0, guess what? Now, we're talking about slopes here, right? Not the value, but slopes, okay? The slope is 0. So I guess those really should be, yeah. But we don't know the magnitude of the slope. We just know that the slope is 0 there, okay? I'm sorry, I said it wrong before. These are slopes here. So these are horizontal little arrows here at every place. But when y is equal to 0, x is equal to 0, that's on the y-axis, your slope is also horizontal, 0 slope. And down here too, everywhere on every axis, your slope is 0. All right, that one was easy. Okay. Let's say 1, 1. What's your slope there? X equal to 1, y is equal to 1. What's your slope? Second? No, here's the thing. Dy dx? 0.2. Okay, the slope, that's a very, very gradual slope. I mean, just a little off there. Okay? How about 1 minus 1? That would be just slightly off horizontal there. Minus 1, 1, that would be over here. That would be, again, just slightly negative. And minus 1, here you go to being slightly positive again. Okay? Pick another one. 2, 1. What would that be? 2, 1. Right where? Say again? 0.4. So that's twice as positive. Okay? Like this. Down here it would be negative 0.4. Okay? Down here, positive 0.4 again, and negative 0.4 again. Okay? How about 1, 2? Oh, I did too much. 0.4 minus 0.4, 0.4 minus 0.4. Is that the one? Yeah. Okay? And you just keep going from there. The further out you get from the origin, the larger your x's and y's, the bigger it gets, meaning the more slope it has. So you look at the book and you get this kind of thing. Okay? All horizontal slopes on the x-axis, y-axis at 0, and then very slightly off that and just off the quadrant there, and then slightly more that you get further away. And after a while, out here some, if we did, what's this, 1, 2, 3, 4, 5, 6, if we did positive 6, 6, 6, that would be up there, what would that be? Point 6, 6. 0.2 times 36, and that's going to be 7.2, right? That's a pretty healthy slope there. And it's paused here. 7.6 up here, minus 7.6 down here, minus 7.6. That's not steep enough. Oh no, there's positive here. Okay. And then minus here. Okay. Well, guess what we've got here? Pretty close to what they got here. That's why I said I don't want to do all these. But you see, you got pretty steep slopes here coming in, rounding up on here because everything flattens out here. So it's negative in this quadrant, positive in this quadrant. The closer you are to 0, the smaller, further out you. And then you do the same thing here, coming up here, going down there. There you have it. And here are some of the solution curves, or the family of curves. Pick a value and follow it through. Okay? Pick a value, follow it through, depending on what your C is. Now, they told you what the solution was. They didn't tell you how to get it, but they told you what it was. Shame on them. I mean, it's just not very fair to do that. Why aren't they telling you how to solve this? Actually, but they say we saw in section 1.1, so we have already done this. But we still didn't know how they got it. This is not the way I like the two differential equations. I'd rather, let's go and show you how to get it. But you see, the book isn't set up that way. Okay? But here's the voila, we probably have done it before. They said, this answer, y is equal to, is it time? How can it be? Okay? I'll just write it for you. Y is equal to e to the 0.1 x squared. That is a solution that will work to solve this differential equation. And then what we do is put our arbitrary constant in C, and for different values of C, you can get different curves on there. Okay? Now, what I'd like to ask you to do is take the derivative of this and plug it into that equation. Where dy dx is going to go on this side once you do it, and then 0.2 times x, and this X is just X, Y is this thing, and see it, I think you'll see that does give you a solution, okay? I think we did that before, if you go back to 1.1. Okay, so we'll begin next time in example 2, okay? And let's see if we went far enough to do any homework exercises here. You can try doing number 1, 3, try doing 1 or 3, okay. And again, this is sort of just look, feel, play around with it, see what you think of it. Okay. Good deal. Have a good weekend.